This is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So we will start in this video that module 2. Okay, so we will see first analysis of thin rectangular plate subjected to bending and twisting. So the lecture topic will be first bending of thin plate and then pure bending of thin plates. So now what is bending of thin plates? So content about topic covered in general, right? What we will see in this video is we define a thin plate as a sheet of material with a small thickness in comparison to its other dimension. Means what? Define a thin plate as a sheet of material. So whatever the material is there of that sheet, having a small thickness. The thickness should be very small compared to the one other dimension. Either it's like suppose rectangular is there. Sheet means rectangular will be there, a square will be there. So their dimension like width and length should be very small compared to the thickness. Then we can say that as thin plate. So let's see again, the dimension stands for here for rectangular beam is what? Width and length. For a square, same length. So that this means whatever this length is there, length of this and this one. So let's see, this thin should be very small, right? Then we can say that is the thin plate. A plate of this type is a fundamental component of an aircraft structure. So where fundamental component means what? These thin plates we are using over the skin of the fuselage, wings, everywhere. So whatever the outside from that you are seeing, that is made up of the thin sheet only, or that we can say that skin of the aircraft or skin of the fuselage. So that is the fundamental component. Without that we cannot cover the aircraft itself. Such as area of stressed skin bounded by adjacent stringer and ribs in a wing structure. So see in a ring, in this one, skin bounded by adjacent stringer and ribs. So adjacent, one stringer is here, another one is here. So this one adjacent bounded by this one, that is called skin, and that is of the thin sheet, stringer and ribs. And in wing structure, so in wing structure, stringer and ribs are there, and adjacent stringer and frames in a fuselage. So in fuselage, what happened? Like here, stringer and ribs, they are just combined. So just here, in wings, structures, stringers and rib will be there, and in fuselage, stringer and frames will be there. So they are supported by what? This thin sheet. So that's why this is the fundamental component, or you can say very basic. Without that, aircraft imagination of aircraft itself is not possible, because if you will not cover, then what happen? That will open only the frames and ribs and the spars will be there, right? So that is the fundamental. In this chapter, we look at how different loading and support condition affect the small deflection of rectangular plate. So in this, what we will see, when we will load or then load will apply on that one, then with what condition, how the supports are there, like support condition, either it's simply supported, cantilever type or whatever, how it's that a small deflection affects, right? So that's it. There are two approaches presented: a perfect theory based on solution of a differential equation and an energy method. So there are two methods. First one is by what? Solution of differential equation. We just form a differential equation of that whatever the shape of the sheet is there, and first form the differential equation and solve that one, then you will get the answer and that we can find. Our second method is energy method. So in previous chapter also we had seen energy method, and in energy method what we had seen, wherever the complex structure is there, we can go with the energy method and we can find the solution for that one. So here again, the complex structure will be there, the shape of the skin. Again, it will be not horizontal, though it's a sheet, but that can be bent, or just like curve type also is there. So for those, what we will prefer? Energy method. So in this chapter, again, we will see by the energy method, only not by the differential equation method. And energy method relying on the principle of the stationary value of the total potential energy of the plate and is applied loading. So here what we will see again, the total potential energy method, which we had seen in the module 1 for the applying loads. Now pure bending of thin plates. So pure bending, okay, pure bending moments of intensity mx and my. So this is mx along the x-axis and my per unit length are uniformly distributed along the edge of the thin rectangular plate. Okay, so mx and my is uniformly distributed throughout the plates, that edge of the plates, not over the entire plate. So this is the plate, this is x-axis, right? Then like this, it's a mx, and here y are uniformly distributed over this full my, and from here to here mx is distributed. The former is applied along the edge parallel to y-axis. So just see, mx is applied parallel to y-axis, so former. While the latter is mx is applied along the y-axis and my is applied along the x-axis, parallel to the x-axis. So sorry, this will be mx and this will be my. When these bending moments produces compression at the upper surface of the plate and tension at the lower, we assume they are positive. So now just see, this is suppose plate is there. Now once we will bend like this. So once we will bend like this, then what happen? This will get stress. So this surface, that outer surface will experience what? Tension. Just see here, this becomes the curve, right? So this inner surface will experience the compression. So outer surface will experience tension, inner surface will experience compression. Similarly with this, like suppose with this we will fold. So this upper surface will get tensed, means it will experience tension, and the inner surface will get compressed. So in that case, that we are taking that as positive, means when upper surface is getting experiencing tension and inner compression, that we are taking sign convention as the positive, and reverse negative. If we also assume that the displacement of the plate in a direction parallel to z-axis is small in comparison to its thickness t. So here we have to assume, because along once we will apply moment along x and y, then some displacement will be there along the z-axis. Okay, so that displacement we are considering that as very small, even comparison to its thickness. So already thickness is very small, and that displacement also even is smaller than thickness. So we can ignore that one. And that section that are plane before bending remains plane after bending. Then a simple beam theory means that we can say after the theory also, after the bending also, and before the bending, that plane remains the same, right? And hence that middle one of that will be only, so here suppose like this is, suppose here it will bend, right? So this side also. So here one plane will be there in between middle of these two, that remains undeflected or undisplaced or not experience any type of bending, right? So this plane, either this side, if you will take along this one, then this plane, and from this side, this plane will be the neutral plane, which not experience, neither experience its tension nor compression. Means that plane remains plane before the bending also, and after the bending also. Means when we didn't apply the bending moment, then also it's straight, and even after applying the bending moment also that remains the plane or straight. So after bending, and as in simple beam theory, the middle plane of the plate does not deform during bending. So during bending, middle plate is not getting deformed and is thus a neutral plane. So that's why the name we are saying that as a neutral plane. Means neutral plane is not getting bent, so it remains same as before the bending and even after applying the bending also. For our axis system, we use the neutral plane as the reference. So now what we will take? Neutral plane as the reference plane. So with that only we will measure or find the things. Now consider an element of plate with side xy and a depth equal to plate thickness t. So side xy means this is x, this is y, the plate, and having this thickness from here to here, it is t. Okay, and that is the depth, that third dimension. Assume that the neutral planes and radii, means whenever having the n radii of curvature are x and y in the xz plane and in yz plane. So n radii, n number of, depending upon where it's getting curved, there the radii will form. Like suppose this plate will bend like this. So here the radius of curvature will be there. So that's why. Assume that the neutral planes and radii of curvature are x and y in the xz plane. So once this one will be there, right? This is. So once this will bend, then that curvature radii will be x. And when in this one, then curvature radii will be y. Okay. Displacement in the positive direction of z or downward axis. Again, as in simple beam theory, the direct strain x and y of elemental lamina of thickness z. So x and y means, now suppose here we will take a small elemental strip. Okay, like here, a small elemental strip of thickness dz or z. So here we have taken z at a distance z below the neutral plane. So this is the neutral plane. So from here at a distance z, we have taken this z. Okay, so along this, or now just see the figure here. Okay, or just we have taken at a distance z from here. Okay, so now just see, for that epsilon x will be what? Z by rho x. Similarly, epsilon in y will be z by rho y. Okay, so this will be the epsilon x and epsilon y. Now we have from the beam theory that already we have seen, Ex equals to 1 by E into sigma x minus mu sigma y. Again, for sigma y, sorry, epsilon y, that is strain in y direction, 1 by E sigma y minus mu into sigma x. So now just see here one common thing. If we are taking along the x-axis, then sigma x we are considering as positive and the other one is negative. Now strain along y-axis, then sigma y will be positive and the sigma x will be of negative. Substituting for epsilon x and epsilon y. So now here we have epsilon x, epsilon y. So just substitute there. So what we have, z by rho x. So epsilon x is z by rho x and epsilon y is z by rho y. That is there, right? Z by rho y. So now let's substitute these two values here. So what we will get? Or this equals to this one, right? Epsilon x, this also. So z by rho x equals to what? 1 by E into sigma x minus mu sigma y, right? So now from here we will simplify. What we have to find? That we have to find sigma x from here. So just cross multiply. So now we have ze by rho x equals to sigma x minus mu sigma y. So what we have to find this one? So take this side. So sigma x equals to ze by rho x minus, sorry, plus mu sigma y. So this will be what? Sigma x in this one. But now to see here, what we got that is different after substituting. So here again we have to remove this sigma y in terms of this one. Sigma x we got ze by rho x. So after removing that one, ez or ze, that we will get 1 by mu square into 1 by rho x plus mu by rho y. Next for sigma x, ez by 1 by mu square into 1 by rho y plus mu y. So just see, when sigma x, then sigma x is free from this one and the other one have this new value, right? Similarly, sigma y is ez by 1 by mu square, that 1 by sigma x. So now this term will be free from this mu and plus mu by rho x. So this is sigma x and sigma y. As would be expected from our assumptions of plane section remaining plane, means what we assume that at the middle plane, like here this one, this plane remains plane, right? The direct stress vary linearly across the thickness of the plate. So now what happened? Direct stress will vary linearly across the plane. Okay, the linearly across the thickness of the plate. So it will vary like this. Their magnitude depending on the curvature. So how much curvature it will form? Just here, it's a slightly it becomes curved. So how much curvature it's a forming, right? That value depends on that one, because that much bending moment will be there. As much as it will form the curvature, that much bending moment will be there. So it depends on what? In another word, it depends on the bending moment of the plate, means how much bending moment we applied. Okay. The internal direct stress distribution of each vertical surface of the element must be in equilibrium with the applied bending moment. So just here, the internal direct stress distribution, whatever inside the direct stress distribution will be there, right? For on each vertical surfaces, because here this also you can see those thicknesses there that are made of very thin small surfaces. So for each surface it will be same. So the element must be in equilibrium with the applied bending moment, means each should be in equilibrium. If any surface is not in equilibrium, that surface will move out or flow off. So for that case, it should be equilibrium. So now what we have to do, we have to find moment. What is the moment? Force into perpendicular distance. So first find force. So force is perpendicular, sorry, moment is force into perpendicular distance, right? So now force is what? In terms of stress. So stress into area into perpendicular distance. Okay, what we have assumed that thickness as z, right? So area will be sigma into area. Area will be what? Z into del y. Perpendicular distance will be what? That del z. So this is the moment right here, sigma x into z del y del z. So this is the moment. Now from where to where? So this is our earlier we are saying that reference plane or neutral plane we will take as the reference. So from here or inside whatever the plane will be there, half will be up and half will be down. So the from minus t by 2 to plus t by 2 thickness, because now we are taking that center as the middle part as the reference. So from reference point go down by t by 2 and go up t by 2. So going down means minus t by 2 and up is plus t by 2. So this will be the moment along the y axis. So that mx, which is parallel to y axis. Mx is parallel to y axis and my is parallel to x axis. Now here sigma x is there, and just now we found that sigma x. Substitute this value there, here. So after substituting, what we'll get? Minus t by 2 to plus t by 2. This is the sigma ez square by 1 minus nu square into 1 by rho x plus 1 by rho y and dz. Now just see here first. This is sigma x value. Okay. So after substituting here, we'll get this as mx. Similarly for my. So the same will be there, but just you have to ez square by 1 by nu. Here this will be only 1 by sigma y and plus 1 by sigma x dz. After that, once we will integrate this one and substitute. So let's integrate this first. So mx, okay, minus t by 2 to plus t by 2. First we are, so e is this one 1 by rho x plus 1 by, this is constant. So let's take out. So 1 by rho x plus 1 by rho y, okay, into e by 1 minus nu square is constant out of integration. Now this is minus t by 2 to plus t by 2 from where to where? Z square dz. Okay, so z square dz integration is zq by 3. So zq by 3 from where to where? Minus t by 2 to plus t by 2. I'm just skipping this one. I'm solving for this only. And later we will multiply. So zq by 3 is t by 2 whole power 3. Okay, 1 by 3 also taken out common. Okay, minus of minus t by 2 whole power 3. Okay, so now here t by 2 becomes tq by 8. Tq by 8 minus, and this becomes tq because this is positive. So here minus t by 2 into minus t by 2 plus t square by 4 into minus t becomes minus tq by 8 and minus plus. So plus tq by 8. So and 1 by 2 is here. Okay. Sorry. Oh, okay. This is 1 by 3, not 1 by 2. Out of this one, zq by 3. So 1 by 3. So now this becomes 2 tq by 24. 2 cancel 12. So tq by 12. Now tq by 12 multiplied here. So let's see here. After multiplying tq by 12, what we will get? After multiplying this, so e tq by 12 into 1 minus nu square, okay, into 1 by rho x plus 1 by rho y. right? So this constant term, consider that as taken as d. Okay, this constant term. So now this big my or mx will be what? D into 1 by rho x plus 1 by rho y. Just this insert, for writing insert, there is no this one. Instead of writing e to by 12 into 1 minus mu square, just insert the written as d, that we can assume that as d. So now mx will be equals to d into 1 by sigma x plus 1 by sigma y, and my will be equals to d into 1 by sigma y plus rho y plus rho x. So now moment along x and moment along y we form, which is parallel. So moment along mx is parallel to y axis, remember, and my is parallel to x axis. So that is the bending moment per unit length along x and y direction are given this one. So let's see quickly once again. So in bending, what happened? So once, according to the assumptions, so when bending will be there, the upper surface will get tensed and inner surface will get compressed. Right. One surface will be there in between that one, which remains constant before the applying bending moment and even after the applying bending moment. That plane we are calling as the neutral plane. So neutral plane we will take that as reference because it's not getting bent. It's not getting affected even by applying the bending moment also. So this our reference plane will not change. So that's why we'll take that as reference plane. So now from there what we assume that here at a distance z from this one, because now we will take this as reference, so we will measure distance from here only. So at a distance z from this point, we have taken that a small elemental strip of thickness that with dz or z value. So here again, as simple beam theory, the direct strain x and y of the elemental lamina of thickness z at a distance, this thickness del z. Is the del z at a distance z below the neutral plane is given by, right here. So now because of that, what will be the deflection? E of x equals to z by rho x and E of y equals to z by rho y. Okay. Now we have from the beam theory again, epsilon x equals to 1 by E into sigma x minus nu sigma y. Similarly, Ey equals to 1 by E into sigma y minus nu sigma x. Substituting for epsilon x and epsilon y. Just equate that one. And after that, what we will get? Here, sigma x equals to Ez by 1 by nu square into 1 by rho x plus nu by rho y, and sigma y equals to Ez by 1 by nu square into 1 by rho y plus nu by rho x. Okay. After that, what we have to do? We have to just find the moment of what? So moment formula is what? Force into perpendicular distance. So first we found force. Force is what? Stress into area. So here stress is there along the x-axis into z del y, that area of that elemental strip, and at a distance of dz. So that perpendicular distance. So now this becomes force. So stress into area. So this is force and the perpendicular distance. Force into perpendicular distance gives moment. So here that as moment mx. From where to where? Because we have taken this as the reference plane. So t minus t by 2 and plus t by 2. From this side minus t by 2 to plus t by 2. Okay, that will be the limit. Now substitute mx for sigma x. So here what we will do? Substitute this sigma x value in mx and sigma y value for my. Okay, so now after substituting, what we will get? Here mx equals to minus t by 2 to plus integral of minus t by 2 to plus t by 2 ez square by 1 minus nu square into 1 by rho x plus 1 by rho y dz. Okay, and similarly my will be equals to minus t by 2 to plus t by 2 ez square by 1 by nu square 1 by rho x plus 1 by 1 by rho y plus 1 by rho x dz. I showed here after solving that, integrating this part, what we got, that constant value etq by 12 into 1 minus nu square after integrating and substituting the value. Okay, so that considered as d, this constant value. So now from this mx will be equals to what? 1 by rho x plus 1 by rho y into this d, and my will be d into 1 by rho y plus 1 by rho x. So here that mx will be d into 1 by rho x plus 1 by rho y, and my is d into 1 by rho y plus 1 by rho x. Where d is what? Et q by 12 into 1 minus nu square. That is here. 12 ETQ by 12 into 1 minus nu square. Okay. So this is again the reference THG Maxim from the aircraft structure, that book. Saying that is your textbook. You can refer that one. Okay. So if you have any doubt, you can just comment on the video or you can contact me regarding your doubt. I will clarify your doubt. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.